In this podcast, we're exploring the science of semiconductors, diodes and resistance. So Ben, let's start there. First of all, what's resistance?
Well, we know that electrical current is the amount of charge flowing through a circuit, and we know that voltage is a measure of how hard the current is being pushed around the circuit. You need a voltage to push the current around the circuit because bulbs, motors and even wires tend to resist the flow of the current. We call this tendency resistance.
And can you relate one of those to the other?
Yes, well, it makes sense that if you want to increase the amount of current that's going to flow, you're going to have to increase the voltage. And also, if you increase the resistance and you want to keep the same amount of current, you're going to have to push harder with a higher voltage. It's a direct relationship, so we can use an equation to work them out. It's voltage equals current times resistance, or V equals IR, because I is used to signify current.
And how well does this actually work, this equation?
Well, for sensible currents in most metals and insulators, which stay at a constant temperature, it works very well. So well, in fact, that we call V equals IR Ohm's law.
And how would I use Ohm's law?
Well, if you had a torch bulb with a resistance of 3 ohms, which needs half an amp of current to light, then you could find out what voltage it needs by using V equals IR. So the voltage will be the current times the resistance, or 0.5 amps times 3 ohms, which gives you 1.5 volts.
Okay, so say I've got a 240 volt heater, and that's got a resistance of 48 ohms. How much current will that draw?
Well, you can rearrange Ohm's law. If you start with V equals IR and divide both sides by resistance, you get V over R equals I. Our new equation says that if you want to increase the current, you can increase the voltage or reduce the resistance, which sounds good to me.
So the current should be 240 volts divided by 48 ohms, and that should be about 5 amps.
Yes, that sounds right to me.
So in my notional heater, where does that resistance actually come from, though?
Well, as electrons move through a material in an electric current, they will collide with atoms in the material. When they do this, they lose some energy to the atom, heating it up and slowing down the electron. So these collisions resist the flow of electrical current, and we say that the material has resistance.
So what affects the resistance of a piece of wire?
Well, the same length of wire with a large cross-sectional area will have a smaller resistance than a narrow wire, as the electrons are being pushed through a bottleneck in the smaller wire.
Okay, so narrow wires have a higher resistance, but what about length?
If you try and pass a current through 2 identical wires connected in series, you double the length and you double the voltage you need to pass a certain current through them. So, doubling the length doubles the resistance.
So in other words, the longer the wire, the higher the resistance.
Yes, and another thing that can hugely alter the resistance is the material you're using. Copper, aluminium and gold are very good conductors. In fact, they're thousands of times better than steel, which in turn is trillions of times better than many plastics, glass, etc. They conduct electricity so badly that we call them insulators. And of course there is the effect of temperature.
And what effect does that have?
Well, it depends on the material. With metals, the hotter the metal is, the more the atoms are vibrating, which means they are more likely to collide with a moving electron, so that means the resistance increases. This means that as the filament in a light bulb heats up to white hot, its resistance will actually increase.
Are there any materials that don't behave like that?
Well, yes, for example, the semiconductor in a thermistor, as that heats up, it will release more electrons available to carry current. So its resistance actually reduces quite significantly as the temperature increases. And that means it can be used as a thermometer. You can use other forms of specialised resistors as other types of sensor. A light-dependent resistor, or LDR, behaves similarly to a thermistor, but instead of heating it up to release the electrons, you shine a light on it. So at low light levels it has a few free electrons and a high resistance, but in bright light it has a low resistance. Another, and far more important semiconductor device is a diode.
And what's that?
Well, it's a device which, if you apply a voltage in one direction, no current will flow, but if you apply a current in the other direction, it can flow with a low resistance. So a diode works like a one-way valve for electric currents. Diodes are very, very important, and many of the small coloured lights you see on electronic devices are a form of diode called a light-emitting diode. Diodes are also the basis of almost all the more sophisticated electronics.